Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the crushing and grinding equipments and how they are modeled in Aspen Plus domain. Now, both the crushing and grinding equipments, they follow the same working principle. Only difference is that crushing equipments are used for crushing the larger size solids, whereas the grinding equipments such as ball mill, etc., they are used for grinding to finer particles, almost in the powdered form. So that is the main difference between crusher and grinder, but they follow the same working principle. So let us go to the Aspen Plus window and check how they are modeled. Now this is the simulation window of Aspen Plus. And if you look at the model palette, then the solid tab will have the crusher over here. Okay, so this is the model for crusher. So if you hover around it, you will find the description of crusher. So it says it's a solid crusher that models gyratory or jaw crusher and cage mill breakers, etc. There are other kind of crusher or grinders are there, like most common is ball mill. Okay, they can also be modeled with this crusher block. Now let us first bring this crusher model over here and let us see how many material streams are there. There are two material streams. One is the feed, that is input, and another is the product stream. Okay. So let us now rename this so that we can understand it better. So we will rename it to feed, and this one we will rename it to product. Okay. So we have one feed stream and one product stream. Now before going forward, we must remember two things. The first one is the phase of calculation. In most of the cases, the crushing and grinding equipments, they handle solid material. Unless there is any slurry, it's a different case. But in most of the case, they handle solid material. So if that is the case, then you have to run the simulation in solid phase only, not in mixed phase. And another thing is that to define this feed and product, you have to use the stream class as solid, either with PSD or without PSD, but you have to add the stream class of solid. So these two things you have to keep in mind. And another thing that is important is the particle size distribution. Okay, both feed and product, they will have their own particle size distribution. But feed particle size distribution may not be known to us. I mean, there is no hard and fast rule that we have to know the feed particle size distribution. But the product particle size distribution has to be either defined by us, the users, or it has to be calculated by the system itself or the model itself. So product particle size distribution is very, very important. Nevertheless, if both feed and product, they have their own particle size distribution and it is known to us, then in a scale, suppose this is a particle size and this is the fraction of particles which fall under certain particle size range, then obviously we will get two particle size distributions. Then this particle size distribution has to be of the feed and this particle size distribution has to be of the product, because the feed characteristic particle size has to be always higher or larger than the product particle size. Okay, because that is the job of a crusher or grinder. It reduces the particle size of feed, right? Now, let us now find out what are the parameters that we have to set for this crusher model so that it works to our desired expectation. So you double click it. Yes. Now here you will find first thing, that is the outlet PSD calculation method. Okay. So there are three methods available. One is by selecting the equipment, whether it is a jaw crusher, whether it's a ball mill, whether it is a gyratory crusher, or whatever. The second one is determine the outlet particle size distribution from comminution power and distribution function. Okay. Now we will understand it later. And the third one is the simplest one, specify the particle size distribution yourself, the user. That means no matter whether the system or whether the crusher is a jaw crusher, or is a ball mill, or gyratory crusher, or hammer mill, whatever it is, I do not have to bother about that. I will give my desired particle size distribution information to Aspen Plus and ask Aspen Plus to calculate accordingly. So let us learn the simplest one first. So first let us specify the particle size distribution. So here you have to select the substream ID first, because if it is a solid stream only, then you have to select solid stream, and then user specified particle size distribution. Now you may have an user specified particle size distribution where you can say that, well, I have the particle size from 0 to 1 millimeter. It will be only 2% of the particle size. 2 to 3, we will have maybe 10%. 3 to 5, we will have 30%, and so on. So you will get a bell-shaped curve, which is the particle size distribution. But we may also define the distribution function. For that, first we have to select a distribution function ID. So we have to create new, and then the distribution function will be open for us. Now here you will see there are various options like normal, log normal, RRSB, that is Rosin, Ramler, Sperling, Bennett function, and GGS, that is Gates, Gordon, Schumann function. So all these distribution functions already you know, because you have attended a lecture which has been delivered earlier. So you can always refer to that lecture and refresh your knowledge. So these distribution functions will be clear to you. For instance, if you use this RRSB function, then you have to select these parameters. So you have to either specify D63 or D50. Either of them you have to specify. D63 means 63% of particles should pass through a mesh size of this value. That is actually D63. Similarly, if you use D50, then it will be regarded as a number or a mesh size. Say if it is a 2 millimeter, that means 50% of particles should pass through a mesh size which is 2 millimeter in dimension. That's what it means. So either D63 or D50 you have to specify. And accordingly, this particular parameters you have to choose. You can choose both D50 and D63. And if not D63, you have to choose RRSB dispersion parameter or stiffness. So whichever you choose, accordingly, this particular parameter display will be changed. Suppose if you use stiffness, then they will ask you what is the stiffness factor. So that you have to specify. Okay? And never forget that for solid handling, you have to use solid only phase. So this is by specifying the outlet PSD. Now the second one, that is determine the outlet PSD from comminution power and distribution function. Now distribution function, obviously you know already what is distribution function, but what is this comminution power? For that you have to go to the grindability and it will be clear to you, and you see the comminution law is specified over here. Now, how many types of comminution laws that you know? You know Bond's law, Rittinger's law, and Hicks law. So these are the common comminution laws are available in the textbook. You can go and refer these laws to understand it better. If you want to refer to the Aspen Plus help file, then you can go over here. Now here you will find all the comminution laws in a single equation. That is dou W is equal to minus C into dou dP by dP to the power n. Okay, where W denotes the work input on a mass basis. That is the ratio of power input and the feed mass flow. That means to perform a crushing exercise, how much power is required per unit mass of material that we are crushing. Generally, it is expressed as kilowatt hour per tons of material that we are handling. Okay, so there is another name for this. This W can also be regarded as specific power. Now, what is dP? dP is the characteristic particle diameter of the produced particle. A relative value for this particle size is dAt. If dAt is say 2 millimeter, that means 80% of the particles that will pass through a mesh size which is 2 millimeter in dimension. That's what it means. So dP is given, and what is n? N is an exponent which is different for each comminution law. N is equal to 2 for Rittinger's law, it is 1.5 for Bond's law, and it is 1 for Hicks law. Okay. For instance, if you take Rittinger's law, then the actual equation will be dou W is equal to minus C dou dP by dP square. Okay. So if you integrate them, you will get W is equal to minus C 1 by dP, and this from feed to product. The crushing began with a characteristic size of dF, that is the feed particle size, and it has crushed to dP, that is the product characteristic particle size, right? So it is from dF to dP. So if you do this calculation, you will find the Rittinger's law as given over here. Okay. The CR, that is the Rittinger's law parameter, is calculated from this equation, 0.5 into 3.6 into 10 EI into dBi to the power minus 0.5. Now dBi, the value is taken as 0.00005 meter, and EI is called the bond work index. Now what is bond work index? Bond work index is defined as work required to reduce the unit weight of a theoretical infinite size to 80%, passing a diameter of 100 micrometer. That means dAt is equal to 100 micron. That is an infinite size of chunk. Practically infinite size is not possible, so you have to assume it's a big chunk of material. How much energy has to be given to break or that solid chunk into particles, whereby 80% of such particle should pass through a mesh of size 100 micron. That's what it means. Okay, so that is the bond work index. And if you want to know how the bond work index is calculated, then you will find all the definitions over here. So you just go through them, or you can go through any textbook of crushing and grinding, you will get them. So let us go back to the comminution laws once again. Here, a table is given to let you know at which condition which law is used. So Rittinger's law is used when the particle size diameter is 0.05 millimeter. Okay, and Kick's law is used when particle size diameter is more than 50 millimeter. But when the particle size is from 0.05 millimeter to 50 millimeter, then bond law is used. So this table will guide you when to use which comminution law. Okay. So let us go back to our simulation window. You have to fix the mechanical efficiency. Now the crusher may not work with 100% efficiency. Crusher efficiency may be 90% or 80% or whatever. So accordingly, you have to write the efficiency within the range 0 to 1. Suppose if the crusher is running with 85% efficiency, then you have to write over here 0.85. Okay. And you have to write the value of bond work index over here. And there is another kind of index, that is Hargrove grindability index. Now here you can define the Hargrove grindability index. So if you define Hargrove grindability index, accordingly the bond work index will be calculated from here. Okay. So either you can give the value of bond work index directly over here, or you can specify the Hargrove grindability index from where the bond work index can be calculated. Okay. And another thing, do not get confused over here, because here it is showing mixed because I have not defined the stream. While solving the example, I will define the stream over here properly. Actually, it should not be a mixed stream. It will have the CL/PSD stream. I mean, obviously, we have to define the particle size distribution also along with this in the solid stream. So that will be changed to CL/PSD or MIX CL/PSD or whatever. And another thing that you have to specify over here, whether the system is open circuit or closed circuit. If it is open circuit, you have to take it. By default, it is taken as a closed circuit, because in closed circuit, the power requirement is less. Now, if you do not remember what is open circuit and closed circuit, actually, for any crushing operation, suppose this is the crusher, you supply the feed over here, then this will be product. Now, in the first run, maybe some portion of the product will pass through the D80 mesh, but some of the product that will still be under crushed. If we give enough power to crush the entire product below D80, then some of the portion of the product will be over crushed. So the best way of doing it, to pass this product through a screen having a sieve size of D80, okay, and get the desired product over here, and whatever the retented portion, that means that is under crushed, that we can recycle it to crusher once again. That means we are not over crushing the material which has passed our D80 mesh size. Okay, so that is how you define your system to be closed circuit. Okay, now by default we assume that it is closed circuit, but if you feel that you want to model it in an open circuit way, then you have to tick it. And needless to mention, in open circuit, your power requirement will be much higher. Now let us go back to our specification tab. So you have specified the comminution law over here. You have to specify the distribution function the way you have done it in the previous case. And you have to set the power specification. How many kilowatt or how many megawatt or how many watt power you want to spend for this crusher operation. So suppose the crusher operates at 2 kilowatts, so you have to give that value. Or you have to give the specific power. That means for 1 ton of feed material, how much kilowatt hour of energy that you spend on that. So that is specific power. So either power or specific power you have to specify. That's how you specify the comminution power and distribution function, and you want to calculate the particle size distribution accordingly. Now, unlike the previous case where you specify the particle size distribution, here you do not specify, but you specify the comminution power law and distribution function and ask the Aspen Plus to calculate it accordingly. And then the first case, that is select equipment. Okay, here you have the option to choose the crusher type. Now, how many types of crushers are there? There are gyratory crusher, single roll, multiple roll, cage mill, jaw crusher, cone crusher, impact mill, hammer mill, ball mill, and rod mill. Now, the upper portion, all the top ones, they are all crushers, and below they are all grinders. Okay. Now, let us learn one by one. Let us choose gyratory crusher. The moment you choose gyratory crusher, so many operating parameters options are open for you because you have to choose them accordingly. Here you will find two options, that is selection function and breakage function. Now, what are they? Why they are required? These are the information that you will get from textbook. I will explain you how they are chosen in Aspen Plus domain. So for that, you have to go to the breakage and selection function drop down menu. You will find two options. One is US Bureau of Mines, another is user specified. For both selection function and the breakage function, you can use either US Bureau of Mines or user specified. Why user specified? Because you may be a researcher, you may have some breakage function or some selection function which you have gathered from open literature and you want to use it, or you may have found this breakage or selection function on the basis of your experimental result and you want to use it in simulation. So you have been given some option to use that user specified function. Or you can use the standard US Bureau of Mines breakage or selection function. What are they? So here you'll find the US Bureau of Mines selection function, and here you'll find US Bureau of Mines breakage function. So let us see what they are. First, go to US Bureau of Mines breakage function. So you will find a table. What is there in the table? You will find 4 types of crushers: multiple roll, gyratory, single roll, and cage mill. You will find all of them at the top 4: gyratory, multiple roll, single roll, and cage mill. Top 4. Okay. Now, here you will find a couple of parameters. What are they? The first one is ratio of product size to feed size. That means a ratio of DP and DF. Now, obviously, DP is less than DF, so the ratio will be less than 1. Okay. Now, suppose that ratio is 0.2 or 0.2065. Then this particular row is open for us. And here you will find feed size by solid outlet diameter, feed size by solid outlet diameter, and this is greater than cutoff, and here it is less than cutoff. So greater than cutoff and less than cutoff. So it is a kind of range that it is indicating. And this range, the less than cutoff range for all crushers, this is the value. For dp by df is equal to 0.2, this is the value. And the greater than cutoff for multiple roll crusher, it is this. For gyratory crusher, it is this. For single roll crusher, it is this. And cage mill crusher, it is this. So these values will be automatically taken by the Aspen Plus. You do not have to add in this value anywhere. Okay? The moment you choose the US Bureau of Mines, these values will be taken. Similarly, let us check what is the US Bureau of Mines selection function, and you will find over here. So here, this parameter will be decided on the basis of whether the crusher is primary or secondary. Okay. Now, whether it is primary or secondary, you have to select in the operating mode. So in this drop-down menu, you will be able to choose whether it is primary or secondary. Now, what is primary and what is secondary? When a crusher is used for crushing a certain material, it is not always possible to use a single crusher and get the outlet particle diameter to the satisfaction level. Okay, so a lot of particles may remain under crushed. So it is always advisable to use crusher in series. Okay, suppose it is a large chunk of material, then a jaw crusher may crush it to smaller chunks, and these smaller chunks may be fed into a second crusher that will make it even smaller particle size, and then finally it can be added into a ball mill. So there will be a series of two crushers and a ball mill to get solid into powder form. Okay. So in that case, the first crusher is called the primary crusher, and all the subsequent crushers are called the secondary crushers. So if you choose a crusher to be primary, then these are the values they choose, and for all subsequent crushers, these are the value the US Bureau of Mines selection function chooses. And what else is needed? You have to define one of them, either the maximum particle diameter, that means the diameter should not be more than that, and then power specification or the specific power, that is per unit mass basis. And the ratio of cutoff size to solid outlet diameter, by default it is given 1.7, but you can set this value to something else if you have a better information. So this is how the parameters are set for gyratory crusher, single roll crusher, multiple roll crusher, and cage mill crusher. All of them have the similar pattern. But if you choose jaw crusher, then you get an entirely different scenario. Here, the selection function changes. There is only one selection function available, that is white and single function. And there are a couple of breakage functions available, either Vogel or Austin breakage function. You can choose from them. Here you have the Vogel breakage function. Now here you see the di denotes the inlet particle size, that is the feed particle, and dk is the product particle size. So this is dp. Instead of df and dp, they are using dk and di. Another parameter is d prime. The parameter d prime is close to the minimum fragment size which can be achieved by the fragmentation. Okay, so these are the this is the minimum fragment size you have to specify over here, and q is the q parameter that also you have to fix, the Q must be specified on the specification C. So if you know these values, obviously you have to learn about the Vogel breakage function in a better manner from the textbook, and then only you can supply these values for your system. Similarly, in the selection function, if you see the Whiten selection function, you will find these two things. The value of SI, it depends upon two criteria, OSS and CSS. What are OSS and CSS? It is open side setting and closed side setting. Now it's a jaw crusher, right? So jaw crusher, basically two jaws are like this. This is one jaw and this is another jaw. So while operating, these two jaws, they move towards each other. And whatever the big chunks of materials are there, they are crushed due to the movement of two jaws. And this is the open side setting. Obviously, open side setting means the highest distance between two jaws, and CSS is the lowest distance between two jaws. Okay? So this is the highest point and this is the lowest point, and so these 2 points you have to specify. Okay, so that's how you define your jaw crusher. Similarly, you can choose cone crusher, hammer mill, and other mills. Let us choose ball mill. It is quite common. In the ball mill also, you have to specify the grindability factors like Bond's law, whether you use Bond's law or some other law, Rittinger's law or Kick's law. And here you have to specify the power specification and the distribution parameters and mill diameter. Now you must be knowing how ball mill works, right? Ball mill means there will be a cylindrical vessel inside which some iron balls will be there, and the materials to be crushed, they are also there, and the mill rotates axially, and as the mill rotates, the iron ball that will go at the top and fall, and due to this impact, the material will be crushed. So that's how the ball mill works, you already know. So mill diameter is important because larger the diameter of the vessel, higher will be the impact and better will be the breakage. Okay. So this is about ball mill specification. Other mills like impact mill, hammer mill, rod mill, either go to your textbook or you can refer to the Aspen Plus help file and you can gain knowledge. So with this introduction, we are ready now to solve some problems. Okay. Now let us open our example.